categorize rotation problems into 5 kinds. Type A rotation is one rigid body. Okay, so this is a single rigid body. You can get complicated, more and more complicated questions because the rigid body is very complicated. So I could say, here is the rigid body rotating about this point. So this is my axis. Rigid body, fixed axis. Alpha. Mass is concentrated here, mg. Maybe there are a bunch of other forces. So find the torque. How will you find the torque? Look at this distance. Look at perpendicular distance. Look at that. You can take that r and then resolve the mg, or you can take the perpendicular distance. So find the torque, divide by I, you will get alpha. Simple. And how will I find what is the acceleration of the center of mass? If this is the center of mass, then you find alpha, you look at this as r. So this is for finding torque. Remember, you need to take r perpendicular, but for finding mg into r perpendicular, whereas for finding acceleration, it is r into alpha. Notice the difference. This is r perpendicular, that is not r perpendicular, just r. Acceleration will point like this. We just did this with the rod, right? Slightly more complex, but not very difficult. This is type A. Very easy kind of questions, right? The only complexity is finding torque, finding I, finding torque, finding I. That you should spend enough time and learn. Okay, that's what we probably did in the basics. Some of you, those who have seen the online lessons, I spent a lot of time on calculating moment of inertia, also on calculating torque, because that is very critical. Now let us go to type B. In this, you have a rigid body which is rotating, let's say something like this, or something like this. The rod is a rigid body. But then I'm not just going to talk about the rigid body, I'll hang from it 2 things. Or I'll take a rope and rotate, go around like this several times and hang from this fellow. This is not rigidly connected to that. Example, here I have exactly such a system. Okay, so if you see this, I have a thread which I am going to wind around this disc. It's a uniform disc, let's assume. And then if I push this axis, I am holding it now, so it's not moving. But if you see what is going to happen, like if I hold it like this, so it looks exactly like the question that I have here. So if you see, this guy is actually exerting a force. That force is going to have a tension here, and therefore it will try to rotate it, etc., etc. And if I now release it, notice what is going to happen. If it was a massless pulley, it's a very different story. But right now we are talking about things with mass, right? So let us start. I'll just show you what is going to happen now. If I leave it, I'm going to leave it from there. See. Right? This has a alpha. Let us try to solve this question. So this is the next kind of problem, type B. Then we obviously we're going to have type C, type D, and type E. Type E you don't have to worry about, but right now we'll only focus on this kind of a question. A slightly more complex version of the question will be if I took this and added a little bit more by putting something on both sides. So let us do 2 questions. I'm going to give you 2 questions. I would like you to solve it. First, this has radius r, it has mass m, this fellow has also mass m. Okay, it is pivoted at the center, it's a uniform disc. Okay, DISK or DISC doesn't matter. What I would like you to do is calculate the following things. So I'm releasing it from rest. Let's assume I release it from rest. So we'll call this A and we'll call this object B. Question 1. Okay, let me write the questions here. Question 1. Find alpha. Question 2. Alpha for what? Because now there are 2 objects, right? I have to talk about alpha for what? This guy doesn't have an alpha. Why doesn't it have an alpha? It's just going down. So this fellow is rotating. So find alpha for the disk. Find, should I ask you to find acceleration of the center of mass of the disk? No, it is 0, it's stuck there. It's already there, not stuck, it's pivoted there. So that you don't have to worry. Find torque on disk. Shouldn't I do that before I find alpha? Yeah. So let's make that question 1. Actually, no. You can do 1, 2, it doesn't matter which way we do. Find alpha is the first question. Find torque on the disk is the second question. Third, find acceleration of A, block A. Is that okay? And then the fourth question is to find the tension, which I don't want to worry right now about. But if you do these 3, let's just first do these 3. Now, with these 3, we will stop. Okay, because I know some of you we have told that we'll finish a little early. But I just want to also show you another kind of problem, which is of very similar nature, which will also be quite interesting. And so this I would like you to try as homework and maybe send it to me if you can solve it. I have 2 of these fellows and both have the same mass. You can see that they both have the same mass. I have put a small set of pins here which you can ignore and say that they don't have mass. Okay, it's just to create a groove. One thread has gone around like this and this mass is hanging from there. The other thread is hanging from this side. Both are equal masses. If I release it, do you think it is going to rotate? mg, mg. Will it rotate? Yes, it will. Because you see this guy has a larger radius, so it will rotate. And so if I leave it, you can see. Okay, so what I will do is I will unwind this a little, so you can see what is happening. Otherwise, it's not easy to see it. Ready, steady, go. So this guy is going down, that guy is going up. That's not the only thing. Okay, I want you to also notice something very interesting. If you see, this guy comes down like that by a much larger amount than that guy goes up. I will show that to you by starting them off at the same level. So they are at the same level now, almost the same level. Watch when after I release. Now I'll just release it so you can see that they are going to go on their own. Okay, so I'll release it. Now they are almost at the same level. I'll release it. You can see what is going to happen. Okay, so I released it from here. This fellow went up this much, but this fellow went down a lot more. Why does this guy go up less and that fellow goes up more? I mean, goes down more. Because this guy's acceleration is not equal to that fellow's acceleration. Both are connected by this angular acceleration. But because the radius here is much more than the radius there, this fellow's acceleration is more than that fellow's acceleration. So we will see all that when we are looking at that problem. At this point, what I would like you to do is to first solve this question. Okay, so shall we start off solving this problem? First point, the torque about this guy is not mg into r. First point, let's keep that in mind. This is mg, but the torque is not mg into r. Why not? Because there is a tension T here and the torque is T into r. There is a tension T here and a tension T here. T is not equal to mg. Why is T not equal to mg? You cannot say torque is equal to mgr is equal to I alpha. Wrong. Why is this wrong? Because the torque is T into r. Why is the torque T into r? Because if T was equal to mg, this fellow won't move down. But if this fellow isn't moving down, how can this rotate? Suppose I say that this is rotating and this is not moving, you will get a slack in the rope. In fact, why is this rotating? Because this guy is pulling. But this guy is pulling doesn't mean that the torque is mg into r, it is still T into r. You need some tension here, right? This tension mg minus T is ma, acceleration of this object. So we need to write it carefully. Let us do this carefully. So this statement will not be correct. So what we should do is to say let this fellow have an angular acceleration alpha. This has a linear acceleration a. Remember that this object's acceleration and that alpha are not connected by r alpha a, all that kind of formula. That r alpha a equals r alpha is for a rigid body, not for this. This is not partly connected to that as a rigid body. It will turn out to have the same formula, but that is because of a special case. Okay, let us think about this carefully. So first, for the rotation, you can say T times R, which is the torque, is equal to I alpha. I is mr square by 2 into alpha. This is the first equation. But now the problem is there is a T and there is an alpha. I have two variables. Okay, let us write F equals ma for this guy. F equals ma for this guy is much more complex because you will have the pivot force, which I don't know. So that will not going to help me much. Let us write F equals ma for this one. If I write F equals ma for this one, I will write m into a. Mass into acceleration downwards is mg minus t. Now I could solve it, but you see alpha is unknown, a is unknown, t is unknown. I have three variables, two equations, you can't solve. So what do I need to do? I need to write a in terms of alpha, but you cannot write a equals r alpha directly, not for this case. And you should be very careful because what I am going to say will end up with a equals r alpha, but you have to think hard about why it became a equals r alpha. Now if I look at this whole thing is rigid. So when this is rotating, this point as it's rotating will have r alpha as its acceleration. So this point has r alpha, this point has r alpha. The point on the disk has an acceleration r alpha. A1 is r alpha. But you are trying to say this has r alpha. We have to figure that out. Why would that be correct? Why will this have a equals r alpha? We'll see. This has r alpha. In fact, if you draw r, this fellow you should actually say is much larger r. Right? It's not this r. I am talking about a point on the disk which has r alpha. But there is a condition that we are using which is very important. No slipping. So I should say no slipping of the rope. The rope does not slip on the disk. So since the rope does not slip on the disk, when this guy goes down by x, this is the part of the rope that has come here. So the rope, which is this part, is moving along with the disk continuously. So the rope there and the disk here, they were moving together. Since they were moving together, they must have the same acceleration. So if this has some acceleration, this point on the disk also has A1 equal to R alpha. Why are these two equal? Because there is no slipping. What will happen if there was slipping? What I am just going to say is not valid. If there is slipping, this is still true, but that won't be true. Second, as the disk turns, this rope comes down. So the rope's acceleration is along the rope and the block's acceleration is along the rope. Isn't that always the case? No. Because if the block was like that, imagine that I am taking something and I am dragging. So if I am pulling something, okay, let us see. I will show it to you with a maybe like a surface. Okay, so here is the surface and I have here this object. This is a complicated part. So if I have this object. Now, if I start to turn this around, can you see that the object is moving? Now the acceleration of the object and the acceleration of the rope or the acceleration of that point on the rope, they are not the same. But anyway, that's a very complicated question, right? So we'll have to think about that separately. But if I look at this, the acceleration of that point on the rope, it's right there. So as that point starts to come down, this fellow comes down, this fellow comes down, this fellow comes down, the block starts to go down. So because this is R alpha, this is R alpha, this is R alpha, this point is R alpha, this fellow's acceleration A is also equal to A1, which is R alpha. This is different from saying A equals R alpha. It looks like A equals R alpha, I know. Okay, but this is a different A equals R alpha from what you know. What you know, this is for rigid body. This is not for rigid body. And it is not for this distance. Here if you say, after some time this guy is going to be here, it's still R alpha. Okay, this point is a different R. This point is a different R. They are all rigid bodies. So you can use A equals R alpha for that different points on the rigid body. Here we are using it for something which is not part of the rigid body. That is because this is equal to this, which is equal to this, which is equal to this, which is equal to that. Now you may think that I am just doing this as like too much. I am telling you something which is actually always going to be true. Not the case. It's not always going to be true. This is actually the confusing part many times in different questions. Here luckily it is the same. So therefore what I am going to do is I am going to replace that A by R alpha. Then I can get rid of this R. One R on both sides I have cancelled. Add, you will get mg total is equal to 3 by 2 mr alpha, because it's mr alpha, that's mr alpha by 2, 1 plus half, 3 by 2. So if I cancel out the m, you can see alpha must be 2g by 3r. That's clear? So alpha 2g by 3r. So we have answered the first part. What is the acceleration of this point? R alpha. So if I do R alpha, 2g by 3. So the acceleration of this guy is 2g by 3. Which means my tension, I can calculate from here or from there, or I can just substitute here. Mr by 2 into alpha. How much is Mr by 2 into alpha? So if I do R alpha, you can see that it is 2g by 3. 2g by 3 is R alpha. So that is, let's write it down. R alpha is 2g by 3. Mr alpha is 2mg by 3 by 2 is mg by 3. So this is mg by 3. Let us check if it makes sense. This is not the torque, okay? This is just a tension. Does it make sense? mg by 3, 2mg by 3 is the net force. 2mg by 3 by mass m, g by 2g by 3 must be the acceleration, and that's what we found, 2g by 3. You need mg by 3 because you want the net force to be 2mg by 3. Okay? The torque on the other hand, tau, torque, is going to be T times R. So it is not equal to mgr. It is T times R. T is mg by 3. So therefore it is mg by 3 into R. So torque is mg by 3 into R. Now many times people will not ask you the other two. They will just say what is the torque on the disc, and the answer is mg by 3 into R. Not, it's mgr by 3, it is not mgr. So please keep that in mind. Okay, so we will stop with this. I hope you have understood this. Okay, I just want to highlight one point. Basically, if you look at those equations that I just erased, it was tau equals I alpha, F equals ma. I'm just writing those two. I would like you to try this question. I'll give you the question. It is a regular disc. It's just that this is a small groove, and I have a rope that is kind of tied that way, and I have a rope that is tied this way. This is my pivot. It is a full disc. So this is a full disc, uniform full disc of mass m. This radius is r, inner radius is r by 2. This is also m, this is also m, that mass is also m. This whole mass is m. I am releasing it from rest. Okay, what are the questions that I would like you to answer? Find alpha, and here is the interesting part of the question. We find A1, A2, all that is fine, tension, I'm assuming you will find all of that. Find torque on disc about center. Torque is always, you have to say about what? about the center. The third part, which is actually the question that I am really interested in your finding. What is the force by the pivot? What is the force exerted by the pivot? Please do complete these questions and send your answer to me at learn@ahaguru.com. If you have solved it, send your working, I will take a look at it. Okay. Please do send your full solution. Take a photo of your solution and send it to me at this email ID. LEARN, learn@ahaguru.com. So we will probably stop with this. I just want to add one small thing that I missed when I was doing the rod question. So I'll just explain that in a second. So when the rod was like this is the previous question. I had done this by doing Fx and Fy, right? Because I said the pivot force can be written as Fx, Fy and Fx. But we had already resolved the force as mg, well this angle was 30 degrees. So it was mg here. So mg cos 30. And we had resolved this as mg sin 30. Because I was doing Fx, Fy, I wanted to point out that there is a force which is Fy. But if you wanted to find F, it was actually quite straightforward. You could have just resolved it in this direction. You could have said, here is one F parallel, and then we are going to talk about something like this. Let us call that F perpendicular. And the acceleration of the object at the center of mass is in this direction, ACM. In this direction, acceleration is 0. ACM along the parallel part is 0. Then you can say F parallel is equal to mg cos theta. Why? Because in this direction acceleration is 0. Not always. If it has a velocity, in fact that is the better way to do it. If it has an angular velocity, okay, let us say omega naught, that means it will have a linear velocity, center of mass will have a linear velocity, in which case it will have an acceleration which is v square by r, or v square by r is how much? R omega square. So you can say acceleration is r omega naught square. It won't be 0. Now it is 0. Then you will say F parallel minus mg cos 30 is equal to m r omega naught square. Ma, F equals ma, the same thing. But I could have done it like this, because then this direction the answer would be easy. Then you don't have to resolve acceleration. Then you can say this force, okay, or this force minus that force, because mg sin theta minus this must be ma. We could have written that as well. We could have done MACM is equal to mg sin 30, which is mg by 2, minus F perpendicular, and then we could have done F parallel is mg cos 30. Mg cos 30 is root 3 by 2. I don't remember now what that ACM was. If you substitute that, you will get the exact same thing. You will find these two, and when you do F parallel square plus F perpendicular square root of, that will have given you the exact same F magnitude. So this is another way to do it. But because the earlier problems, all of them I did Fy and Fx, I wanted to just continue in the same style to tell you that you will, once the rod turns like this, you will have an Fx as well. Of course, you can, just to solve this problem, you could have resolved it in these two directions. Anyway, so we will stop with that. Please do try this question. I hope you found the session useful. If you have any comments, please do send. I will be there looking at it for a little bit more. But we are going to close the session with this. So thank you very much.